When asked to describe my research interests, I return over and over to an interest in how teachers think about the content they teach. I am using my dissertation titled Combinatorial Meaning for Algebraic Structure, Lessons from a Design Research Cycle to explore this interest, specifically related to algebra teachers thinking about algebraic identities and related mathematical topics. I am completing this work under the direction of Dr. Eric Tillema. My dissertation study itself is an iteration of design research that fits with Eric's work and within the larger GammaCat design research project funded by NSF. The purpose of this poster presentation is to discuss the methods that I have used in my dissertation study. Thank you for stopping by this virtual space. Two broad goals have guided my study: supporting mathematical thinkers to develop mathematical meanings as personally powerful, and leveraging personally powerful meanings in the teaching and learning of algebra. I have used two studies within my dissertation to work toward these goals. I begin by defining what I mean by mathematical meanings, introducing the personally powerful distinction, and situating these constructs in the mathematical content of this study. I follow Pat Thompson and colleagues' definition of mathematical meanings as the space of implications that the current understanding mobilizes, and Capit's framework for algebra, which situates three content strands within two core aspects. These core aspects characterize algebraic reasoning as fundamentally about making and reasoning about statements of generalization, in this case, the cubic identity for binomial expansion. I see core aspect A, making the statement of generalization, as establishing the understanding that is the core of the meaning, and core aspect B, reasoning about the generalization, as vetting the meaning's space of implications. I use the image above to illustrate the integration of these frameworks. I use combinatorial meaning for algebraic structure to indicate thinking about algebraic identities as a generalization of combinatorial and quantitative reasoning. I consider a combinatorial meaning to be a conceptually grounded class of meanings for algebraic structure that has the potential of developing into a personally powerful mathematical meaning. Within the core aspect A bubble, you see the card problem task, which served as the basis for generalizing the cubic identity in both studies. Indeed, the learning trajectory began with establishing coherent combinatorial reasoning for the quantitative problem scenario. What I mean by coherent combinatorial reasoning is anticipating that a systematic counting process should be evident in a representation of a set of outcomes and also in the expression determining the cardinality of the set. Within phase 2, participants generalized the cubic identity across multiple iterations of the card problem, and phase 3 involved applying the reasoning to purely symbolic problems, including treating the algebraic expressions within the identity as objects of combinatorial reasoning. In study 1, I used a teaching experiment to support 2 veteran teachers to develop a combinatorial meaning, and from that perspective, explore algebra topics they saw as related. This served to develop the pedagogical potential of their meanings and of mine as well, which was important for study 2, where I acted as a classroom teacher operating from a pedagogically powerful combinatorial meaning for the purpose of supporting students to develop a combinatorial meaning of their own. In study 1, I used levels of combinatorial understanding, Tillema and Birch's planes of learning, as a lens for analyzing how the teachers reasoned about symbolic algebra tasks. There were distinct differences in Brooks' algebraic reasoning and Paul's. These differences can be mapped back to their respective levels of combinatorial understanding in quantitative contexts. Brooke at level 1 and Paul at level 3, where level 3 meets the criteria of a personally powerful mathematical meaning. Finally, to analyze my own instruction and interactions with students, I used Wasserman's framework, which aims to categorize the application of mathematical knowledge in the work of teaching. What I'm finding through this study is that as a teacher, I not only engaged in these actions myself, but I asked students to engage in them as well. Instead of, for the purposes of removing complexity, I was supporting students to manage it. Similarly, instead of highlighting complexity, also called decompressing, I was supporting students to develop it.